Hello all. I welcome you all back to the session on chromatography. In this particular module, we will discuss about the retention index and the retention volume. Retention index is a solute characteristic parameter for any individual compound which is present in the sample. And the retention index will be expressed by means of a chromatographic column. If you use different column, for the separation of the same solutes present, same group of solutes present in the same sample, the retention indices will be different for different columns. So if you use one particular column, the retention index will be one particular value, and in some other column, the retention index value will be different. The retention volume is a mobile phase characteristic with respect to the solute's quantity. What is the fraction of the solute it is going to be retained in the chromatographic column? It is expressed by retention volume. So these two parameters, let us discuss in this particular module. So retention index can be denoted by the symbol IX or I, and it is usually for any normal alkane. The retention index will be usually equal to 100 times the number of carbons present in that normal alkane. And this is regardless of the packing material, that is the stationary phase. Whatever the stationary phase which is present in the column, the retention index will be almost equal to n into 100, where n is the number of carbon atoms present in n alkane. And if you multiply the number of carbon atoms with n with 100, suppose xn you take, there are 6 carbon atoms, fn you take, there are 7 carbon atoms. If you multiply 6 by 100, that is 600 will be the retention index. Approximate retention index value for xn will be 600, for fn it will be 700, like this. So retention index will be obtained, and that is regardless of the column packing, irrespective of the column packing. So the calculation of the retention index is very important for any separation scientist, because which chromatographic column is the most suitable one for the separation of group of solutes present in sample. So if the retention index is highly satisfactory from a typical chromatographic column, then only we can recommend that particular column for doing the separation process. Therefore, the retention index value must be calculated. The calculation or determination can be done by using the chromatograms. So you will introduce a sample containing variety of the solutes present in that. And at the end of the chromatographic separation, you will have the chromatogram, and chromatogram will be having number of peaks. And these number of peaks are for different number of solutes present. If there is any unknown solute present in the chromatogram, and the peak for the unknown solute can be obtained to calculate the retention index. And the minimum requirement to calculate the retention index is, in a chromatogram, at least there must be 3 peaks. One should be before the peak of the unknown compound, and after the peak of the unknown compound, there must be other. So the retention times of first and last eluted species must bracket the retention time of the unknown species. So if this is obeyed, chromatogram can be used to calculate the retention index by the mathematical way. So let me demonstrate this. The retention index IX will vary by several hundred retention index units with column variables. If column variables are varied, the retention index will also be varied. So if you use different columns, the retention index will be different. Therefore, the suitable column which is going to produce a specific or accurate retention index value must be chosen for the separation process. So there are 2 methods we will follow to calculate the retention index. One will be graphical method and the other one will be mathematical method. So what is the use of this determination of retention index? It helps to identify the species based on number of carbon atoms. So retention index value will help us to judge how many number of carbon atoms present in that. Based on that, we can compare the retention index with any standard, and we can assume whether this particular compound is present in the sample or not. So you have a standard to obtain the chromatogram for that, calculate the retention index, and you have the sample, obtain the chromatogram for the solute peak from the sample, calculate the retention index, then compare. Same column you have used, same experimental condition you have followed, and the retention indices for the solute from the standard and solute from the sample are resembling, then you can assure, you can easily identify what is the species present in the sample. That's what the usefulness of the retention index. And this retention index is also known as Covatt's retention index. And this Covatt's retention index can be calculated graphically. How do we do this? We know adjusted retention time. So adjusted retention time, we know. What is adjusted retention time? That is the difference between the retention time and the dead time. TR minus TM, you will get adjusted retention time. And you take known N-alkanes, they are standard N-alkanes. Say 4 to 5 N-alkanes you take. And in those alkanes, you know number of paraffinic carbon atoms. So all those N-alkanes have been eluted by means of a chromatographic procedure. You have obtained the retention time for all those N-alkanes in the form of TR. And TM is also available in the chromatogram. You calculate the TR dash, that is adjusted retention time. So TR of solute 1, solute 2, solute 3, solute 4, solute 5, etc. All these solute 1, 2, 3, 4, 5 are alkanes, N-alkanes. So retention time, you know, adjusted retention time you have calculated. Then number of carbon atoms in all those paraffinic compounds, you know, plot the graph of number of paraffinic carbons and log of TR dash, log of adjusted retention time. If you plot a graph, you will get a linear curve. You will get a linear curve, number of paraffinic carbon atoms with respect to log of adjusted retention time. You will get a linear graph. And similarly, for the unknown, you have the retention time. Calculate the adjusted retention time for that too, right? If the unknown 1 is having the log of TR dash here, and for the unknown 2 log of TR dash is here, you extrapolate that and interpolate to the x-axis, and from where you can get how many number of carbon atoms present. Here, if it is 6.3, 6.3 means 6 carbon atoms will be usually present in the unknown compound 1, and 7.3 means 7 carbon atoms will be present usually in the unknown compound 2. So this is how the graphical method can be used to calculate Covatt's retention index. Retention index are also known as Covatt's retention index. This can be obtained by graphical method. Very simple. You have the chromatogram, tabulate the retention time, and you know the standards taken, and all these standards are paraffinic compounds. They are N-alkanes. Number of carbons present in all these N-alkanes, you know. Tabulate the number of carbons present in all these N-alkanes. In another column, retention time. In another column, adjusted retention time, TR minus TM. In another column, log of TR dash. Adjusted retention time is TR dash. So you plot log of TR dash as a function of number of carbon atoms. You will get a line. You will get a line, not necessary to pass through the origin. And similarly, you have the unknown compounds with known retention time. You calculate the adjusted retention time for those two, and you obtain the number of carbons from the graph. Let me illustrate this by the graphical method. So you have a chromatogram. Obtain the data from the chromatogram for all the compounds which are having 4, 5, 6, 7, 8, 9 carbon atoms. So you have passed all these N-alkanes to the chromatographic column, same column, and they have been eluted at these retention times denoted by seconds. Retention time for compound having number of carbons 4 is 62.1 second, And for compound with 5 carbons, 137.9 seconds, and similarly 6, 7, 8, 9, these are all the retention times. And unknown compound 1 and unknown compound 2 were also eluted at 170.5 and 112 seconds. So these two you can obtain from the chromatogram. These are the standards, you know them, because you intentionally eluted these standards from the chromatographic column under some defined experimental procedure. Similarly, under the same experimental procedure, unknown 1 and 2 have also been eluted and their retention times have been obtained. Right. So you have the chromatogram. The mobile phase has given the peak at 12 seconds. So that is considered as TM, dead time. This is required. Why this is required? This is required to calculate the adjusted retention time. Adjusted retention time means RT dash or TR dash, that is also expressed in seconds. This is nothing but RT minus TM or TR minus TM. So you tabulate for standards as well as unknowns. Then you take log for this. You have one more column. Log of 50.1, you will get this. Log of 125.9, you will get this. Now this is the dependent variable and this is independent variable. You fix this into x-axis 4 to 9. You fix this into y-axis. Plot the graph. So you will get this graph. So number of paraffinic carbon atoms will be 4, 5, 6, 7, 8, 9. And log of TR dash will be 1.7, 2.1, 2.5, 2.9, and 3.4 and 3.9. You have plotted this. You will get a line. And for unknowns, the log of RT dash will be 2.2. So you obtain the point 2.2 here. You draw a line to the linear curve and interpolate the point of intersection to the x-axis. Number of paraffinic carbons present in that carbon you will get. And similarly for the unknown 2, 3.15, you locate the point 3.15 here and go to the x-axis, find out the number of carbon atoms, multiply that by 100. So this into 100 or this into 100, you will get retention index for unknown 1 and unknown 2 respectively. So this is how the graphical method can be followed to calculate Kovacs retention index. The requirements are you need a chromatogram from which you can obtain the retention times and the dead time, by which you can calculate the adjusted retention time or corrected retention time. Then number of carbon atoms present in the standards you must know. Log of adjusted retention time you calculate and the plot the graph. Then you calculate log of RT dash for unknown compounds. Then you obtain the number of paraffinic carbons from the x-axis, multiply them with 100, you will get retention index. Right. So here are the number of paraffinic carbon atoms obtained for unknown 1, that is 5.3. For unknown 2, it is 7.3. Right? How to calculate the retention index? The retention index for unknown 1 can be calculated by just multiplying 5.3 into 100. So you have used this data presented in the table. You have plotted the graph. This is the line obtained. This is the line obtained. And by drawing a line to the linear curve from the y-axis with respect to the log of RT dash, you have obtained the number of paraffinic carbon atoms, that is 5.3 for unknown 1 and 7.3 for unknown 2. You just multiply them by 100 because the retention index can be defined as it is multiplication of the number of carbons in normal alkane by 100 will give you the approximate retention index. Therefore, 5.3 into 100, it is 530. 7.3 into 100, it is 730. 730 it is, not 7,300, it is 730. So unknown 1 and unknown 2, you will get 530 and 730 as approximate retention indices for the unknown compounds present. So this retention index will be different for different columns. Right? This is Kovacs retention index. Use the data presented here to calculate the retention index for one hexane. So here the data is presented in this particular table for the elution of air, N-pentane and N-hexane. N-pentane has a number of carbons 5, N-hexane has a number of carbons 6. and air was eluted. This is the mobile phase peak. So dead time is 0.571 minutes. N-pentane was eluted in 2.16 minutes. N-hexane was eluted in 4.23 minutes. Right? And 1-hexane, it is having number of carbon 6. So it was eluted in 3.15 minutes. So RT dash you calculate. For air you cannot calculate. RT dash you can calculate. The values can be obtained. Similarly, log RT dash can also be calculated. Plot the graph. Then calculate the retention index for 1-hexane. So from the x-axis, you will get 5.5 number of carbon atoms into 100. You will get 550 as the retention index. Similarly, you can proceed to calculate the retention index for the unknown compound, right? So which has been eluted in 9.36 minutes by using a column containing 20 molar carbovax as the stationary phase. Standards used in this case is N-pentane and N-hexane. Unknown compound was 1-hexane, for which you calculated the retention index. Here, the unknown compound was eluted in 9.36 minutes. What is the retention index you have to calculate? The standards used were pentane, hexane, heptane, octane, and nonane. You know number of carbons which are presented in the bracket 5, 6, 7, 8, 9. So you elute all those one by one and tabulate the retention time from the chromatogram. You will have chromatogram at the end of the separation. So retention times you have, adjusted retention time you tabulate, log of adjusted retention time you also tabulate. Unknown compound was eluted at 9.36 minutes, RT dash will be 8.57. That is 1.99 minus 0.79, you will get 1.2. 4.47 minus 0.79, you will get 3.68, etc. So log of RT dash, you will get 0.93 for unknown compound. So by using Coates retention index calculation method by graphical way, you can calculate the retention index. You do this, you try. As an exercise, I have presented this. So this is how retention index can be calculated graphically. Even mathematically, the retention index can be calculated in two ways. Whenever the same temperature is followed to elute all those species, this is the expression will be used. Whenever different temperatures were followed to elute all these different species, this is the expression can be used. Okay, how do we proceed? Mathematically, the retention indices for any given compound can be calculated by using two important expressions, and they are used under isothermal and non-isothermal conditions. The retention indices calculated under isothermal conditions is isothermal retention indices. Under non-isothermal conditions, they are non-isothermal retention indices. So retention index denoted by AX is equal to 100 into N plus 100 into log of Tx minus log of Tn divided by log of Tn minus 1 minus log of Tn. What is this? In order to calculate by using mathematical expression, you should have a chromatogram. Not only chromatogram, suppose this is the peak for the unknown solute, for which you have to calculate the retention index. So there are peaks must be present in the chromatogram before the unknown solute and after the unknown solute. Assume this is the unknown, this is the unknown. There is a solute eluted before the unknown compound and after the unknown compound. At least two solutes must give a peak at before and after the elution of the unknown compound. So after the elution of unknown compound, there is a peak, and before the elution of the unknown compound, there is a peak. So the retention time for the unknown compound is denoted by Cx, and the retention time for the solute eluted before the unknown compound is Tn, and the retention time for the solute eluted after the unknown compound is Tn minus 1. You must remember. So the retention time of Tx, solute X, unknown compound, is bracketing the retention times of solute eluting at before and after the unknown compound. So Tn and Tn minus 1 is bracketed for solute X, retention time of solute X. So Tx is the retention time of unknown compound. Tn is the retention time of the compound getting eluted first before unknown compound. Tn minus 1 is the retention time for the solute getting eluted after the unknown compound. So these are all can be obtained from the chromatogram. So for mathematical method, TM is not necessary. TM is not used. Where n is the number of carbon atoms present in the compound getting eluted before the unknown compound. Before the unknown compound, right? So Ix is equal to 100 into n plus 100 into log of Tx minus log of Tn divided by log of Tn minus 1 minus log of Tn. Tx you know from the chromatogram, Tn you know from the chromatogram, Tn minus 1 you know from the chromatogram, n you know from the standard. N you know from the standard. How many number of carbon atoms present in the standard, right? You substitute n you know, Tx you know, Tn you know, Tn minus 1 you know, you substitute, you will get the retention index. This will be in multiple of 100. So for any compound, you can calculate the retention index, and this is okay under isothermal condition. Means if you have eluted all the compounds under the same temperature, especially in gas chromatography, this expression can be used. And when you go to non-isothermal elution, this equation can be simply modified, but without logarithmic term, you can write. All other things remain same, but you don't use logarithmic term. So Ix is equal to 100 into n plus 100 into Tx minus Tn divided by Tn minus 1 minus Tn, which is equal to 100 into Tx minus Tn divided by Tn minus 1 minus Tn plus n. So this is also an expression which is used to calculate the retention index under non-isothermal condition. Okay. So if you have here from the chromatogram what I have presented here, I have been summarized in the form of a table. Use the retention data given below and calculate the retention index for one hexane. So the retention times were obtained 0.571 for mobile phase peak, that is denoted by Tm. Tn is 2.16 minutes. Tn minus 1 will be 4.23 minutes and Tx is 3.15 minutes. So these two columns you can obtain from the chromatogram. You have a chromatogram. It has 4 peaks. First peak is for the mobile phase peak here. This is for the mobile phase peak, and this is for the solute, that is n-pentane, and this is for Tx, that is 1-hexane, and this is for Tn minus 1, that is n-hexane. Because 3.15 is in between 2.16 and 4.23, so this would be unknown. So Tr you know. So you identify which is Tm, which is Tn, which is Tn minus 1, and which is Tx. 1-hexane is the unknown compound, so that is Tx. Tn minus 1 means the compound eluted after the unknown compound. Tn is the retention time for the solute eluted before the unknown compound. So 2.16 is less than 3.15. So this is the solute going to be eluted first than the unknown. And this is greater than this. Therefore, this solute is going to be eluted than this. You just substitute. You know Tn, Tn minus 1 and Tx. Under isothermal condition, you can calculate. So if you simplify, you will get retention index for 1-hexane will be 656. 656. So you can verify this. Number of carbons present is 6. If you multiply this by 100 by Kovacs retention index method, that will be around 600. So 656, very close to 600. So values are satisfactory. So retention index will be 656 under isothermal condition. For non-isothermal condition, the equation you can use is this one, and if you use this equation, you will get 648. There is no much difference. So whether you elute under isothermal condition or non-isothermal condition, the retention index will be almost similar. So this is how the retention indices can be calculated. So this table illustrating the dependency of the packing material or the stationary phase on the retention index. Say for example, acetyl naphthalene will be the compound to be eluted, for which what is the retention index when we use different stationary phases. Polydimethyl siloxane, if you use polydimethyl siloxane, or 5% phenyl polydimethyl siloxane or polyethylene glycol. So this is most polar. This is most polar for acetyl naphthalene. This is the most polar stationary phase. This is less polar than this, and this is less polar than this. So the temperature followed is 140 degrees Celsius for polydimethyl siloxane, and quite usual temperature were followed while using these stationary phases. What are the retention indices for acetyl naphthalene under these different chromatographic conditions? Means under the usage of three different stationary phases: 1460 for PDMS, 1500 for 5% phenyl PDMS, and 2084 for polyethylene glycol. Same compound, different stationary phases, different retention indices. Why? Therefore, by means of this, we can conclude that the retention index for any compound is dependent on the column. So different column, different stationary phase will yield different retention index. You should not forget this. So this is about the retention index, and it is also dependent on the temperature. Next factor is retention ratio. This is also solute characteristic. So what is retention ratio? Retention ratio is simply the fraction of compound in the mobile phase which is going to be retained, right? So it is a degree to which the solute retained in the column. What fraction of the compound out of overall retained by the mobile phase is the retention ratio, or it is the degree to which the solute is retained in the column. Simply, we can write it in a ratio. Retention ratio is simply the ratio of amount of solute in the mobile phase to total amount of the solute. What is the total amount of the solute you have introduced to the chromatographic column, out of which how much retained by the mobile phase? If you take the ratio, that is the retention ratio. So the amount of solute in the mobile phase is simply concentration into volume in the mobile phase. Concentration of the solute in the mobile phase, that is Cm, and volume of the mobile phase, Vm. Total solute is concentration of the solute in the stationary phase into volume of the stationary phase plus concentration of solute in the mobile phase into volume of the solute or mobile phase volume, right? So you divide both numerator and denominator by Cm. So, and after rearrangement, you will get R is equal to Vm by K into Vs plus Vm, where K is Cs divided by Cm, right? Where K is Cs divided by Cm. So K into Vs plus Vm you will get, where Cm will be getting cancelled. Here also Cm getting cancelled. Vm divided by Cs divided by Cm into Vs, right? Plus Vm. So Cs divided by Cm will be K. K is partition ratio, right? So Vm divided by R is equal to K into Vs plus Vm. So this can be written as Vr, that is equal to K into Vs plus Vm. So this expression, you know, R is equal to Vm divided by K into Vs plus Vm, where Vm is the volume of mobile phase, Vs is the volume of stationary phase, K is the partition coefficient, Vr is the retention volume. So what is the volume of the mobile phase to retain this much fraction of the solute, right? Thus, the movement of solute in the column is determined by values of K. Partition ratio is very important to express what fraction of the solute has been retained by the mobile phase and what fraction of the solute is left over in the stationary phase. So partition ratio is very important. Let me demonstrate this by means of a numerical problem here. So you have to calculate the difference in retention volume for solute A and B. They are passing through the column containing 2 ml stationary phase and 3.1 ml mobile phase. The partition coefficient of A and B are given as 8.5 and 16.8 respectively. So you know Vr is equal to K into Vs plus Vm. Vs is given, Vm is given, K has also been given for both the solutes, right? So first you have to calculate Vr. Vr for solute A is Vm plus K into Va. K is 8.5. Va is 2. Vs is 2, right? Volume of stationary phase is 2 ml, volume of mobile phase is 3.5 ml. So 20.1 ml is the retention volume for solute A. Similarly for solute B, if you put 3.1 plus 16.8 into 2, this should be 3.1. 3.1 plus 16.8 into 2, you will get 36.7. Vm is the mobile phase volume, that is 3.1 given. And Vs is the stationary phase volume, this should be Vs, that is 2. And Ka is the 8.5 for solute A, and Kb is 16.8 for solute B. You just substitute, or retention volume for solute A will be 20.1 and retention volume for solute B will be 36.7 ml. What they're asking difference in retention volume. You will get 36.7 minus 20.1, 16.6 ml. So resolution can be improved. At least 16.6 ml of the mobile phase must be passed to elute two successive solutes, right? So therefore, this is about the retention volume. So retention volume is nothing but it denotes the fraction of the solute present in the mobile phase. Assume 1 millimole of the solute has been introduced to the chromatographic column. Maybe 0.5 millimole of the solute might have been distributed equally between stationary and mobile phase. The retention ratio will be 0.5 divided by 1. That is going to be 0.05. 0.5. So this is how the retention volume can be calculated. Thank you very much.